Okay, so we're talking about right now about functions of the variables and the meaning of the derivative. So the derivative of a function of two variables is what right now being considered. Okay, so before we do the algebra, we'll do some, and before we do the spreadsheet, let's just go all the way back and take a look at the what function looked like. And here, this is the function. So we sampled our function of two variables with that formula. These are the 6 values, and we did plot the graph of the function itself. But really, right now we're looking at the meaning of the derivative as a rate of change, and the idea is to look at the rate of change into the two directions. There are two directions, two variables, two directions. You can go either vertically or horizontally within this table, and then that's what we are concerned with. So we already know that in this little table, we already have 6 functions, and if we just let's do it one variable at a time. So if we just look at, for example, the dependence on, what you have circled here, we have circled here is the function of, and z depends on y. Okay, that circled over here. So the x and y's are on the left, that column, and the column on the right, those 3 numbers are the values of z. Okay, so and once again, if we remember, we that's also visible here if it is one of the wires of the wireframe. So that is what I'm talking about, and there's just more data here, and it's slightly harder to handle. So that's why I want to start here with so few numbers. And we already looked at it, and we know that the rate of change is 1 as we progress along the x-axis, y-axis, and along the z values as well, with this little function of one variable. The derivative will be the same from 0 to 1. That's the rate. That's the change of y. The change of z is from 1 to 2, which is also 1. 1 over 1 is equal to 1. Okay, so let me do this again. Let me copy and carry out the whole thing. Okay, so we'll have to start over. So 135, 135. Okay. 135, 0, 1, 2, and these are x's, these are y's. 1, 2, 3, and we add vertically is 3 and 5. 5 and 6, 7. Wait a minute. We're adding 2. No, we're adding 1. Okay, so 0, 1, 2. 1, 2, 3, 4, 5, 5, 6, 7. Okay, that's all we know. We want to plot these. Now we could plot those 9 points above this plane. So this is my xy plane. I built z as the 3rd dimension. We can certainly see the change in that along that line as we did, but we can just as well look at numbers. And let me look at them separately. I'll start with x this time. So this is what I'm looking at. This is what I'm looking at. Let's put it this way. This is what I could look at, and that's a function of x. Z as a function of x. Okay, And we know how to deal with those functions. We know the derivative, so dz dx will be here, as we discussed yesterday. It will be, let me pick one. 3 minus 1 over 1 minus 0. Okay, you see what I did? All right, so the change of z over the change of x. Okay, so it is how the way we compute the average rate of change, but since the function is linear, then it is the same as the derivative. That's very convenient, and we have 2 over 1, or it is equal to 2. Okay. Similarly, we do this was the first transition, the first segment. Along the first segment, the rate of change is 2. The second one also, once again, dz dx. Let me put it this way. Well, let's just keep it. It is 5 minus 3 over 2 minus 1, and once again it's 2 over 1, so again 1. Okay? So that is just one out of those 6 functions. Okay, so this is what we have acquired. It's just that. Okay, so so you don't want to compute and then just have written that all over the place and not knowing where to put it. So let's start forming a table that will contain those numbers. Okay, this is what I'm going to be doing. Okay, so I'm putting x's here. I am putting the values of x still the same, but I will be just like we did it yesterday, I will be ignoring one of the columns, because as you can see, I end up with only 2 numbers instead of 3. Okay, so that is if we do it computationally, that's what happens. We have less data for derivatives because there are fewer segments than points. Okay, so this is what I'm going to do. I put 2 and 2 here. Okay, so those that's 2 over here. Those two 2's end up over here. So that's the rate of change of z with respect to x with the value of y fixed at 0. Okay, so once again, this one is y is equal to 0, y is equal to 0. In addition, x is equal to here. I'm choosing 1. X equal to 2. Okay, so remember those vertical lines are used to deal with a function that is defined without there is no name for the function but only the variable. So I'm talking about z with respect to x. There is no function other than z itself. Okay, so then to indicate where I'm doing computation, I use this vertical line with just writing what my variables are. So in other words, dz dx depends on two variables. So we're going to have a whole table over here, and they will be dependent on x and y. So each time this is all the data we have, but we can for each location we can transition. If suppose we're only going vertical, going only horizontal, and still look at how many transitions we have to make. Like this. So we will have six transitions, and therefore there will be 6 numbers, okay, in the derivative. So rates of change, not only the direction that we picked for the time being equal to x, so we're going horizontally, but also each location might hypothetically produce a different number, okay? So it just happens that it does not, because as you can see from 2 to 4, once again, the change of z is 2 divided by 1. I will be getting 2's all over the place. Okay? Stupid. 0, this is 1, 1, and 2. Okay? So what is this? We call this the partial derivative of z with respect to x. And what is it? It is once again a function of 2 variables. So it's a table. If we do it for every single real value of x and y, it will be literally a surface. Okay. For the time being, I just want to avoid dealing with limits as much as possible, and then this is what we end up with. Just rate of change along the horizontal direction at the x-axis, along the horizontal direction of this particular table, and we computed the rates of change for all of those segments, from 0 to 1, and from 1 to 2, that's for x, but then for each value of y, we hypothetically might get different numbers. Okay, so that is one. The second one is we choose, this time, we choose z to be a function of y. Okay, so z as a function of y. Okay, the results are exactly the same in the sense that the procedure for computing it is exactly the same. So we go in, but except we're going vertically this time, so like this. Through the same table, as you can see how many relations appears from those 9 numbers, we have so many relations between these numbers. We're looking only at the adjacent entries. So we progress over here, the independent variable, which is this time y, progressing from 0 to 1, from 1 to 2. In the meantime, the values of z in the table progress from 1 to 2 to 2 to 3, and certainly there is no doubt that the answer will be 1. So I'm choosing the first, what I marked over there. I'm choosing x equal to 0, what I circled, and y equal to, initially equal to 0, 2. Okay? So then, and then it will be 2 minus 1 over 1 minus 0, which is equal to 1. And similarly, I will within the same circle table. I'm now looking at these two, and so I'm talking about dz dx with x equal still 0 and y is equal to 1. And I have, what is it? 3 minus 2 over 2 minus 1. It is once again 1. Okay? So once again, I don't want to write this out. This is a notation that certainly is legitimate, but remember that when you have so much data, you want to put it in some compact and manageable form. So I'm creating another table, and this one will be all filled with ones. X. I'm sorry. This is y. This is x. 0, 1, 2, 1, 0, 1, 2. I'm skipping the first row, and I'm putting ones here. So once again, this is a partial derivative. So the partial derivative of z with respect to y, and once again, a function of two variables. Okay, so that's pretty much it. The two functions of, we would create two new functions of two variables. Okay, somehow their combination is understood as the derivative of our original function. So how we combine them? We combine them in pairs once again. So since locations, for example, locations x, y are the same, I could combine the value of x and y appropriately. For example, I combine this one and that one. So this one and that one, and it will be 2, 1. A pair of numbers for each location. It will indicate a particular direction of particular importance on the xy plane. But at this time, let's just say we have produced two new functions of two variables. So they also can be plotted with graphs in this particular case, because the original, actually it's interesting to compare to calculus 1, what we just discovered. So can you compare what we did to calculus 1, considering that the nature of the original function versus the nature of the two new functions? How would you characterize the original function in terms of growth or change? It's linear. The function is linear, and in the meantime, its derivatives are what?
Linear, constant.
No, constant. Constant. It's very much like in calculus 1. So the function is linear. So its derivative, or derivatives, I don't want to talk about multiple derivatives. Let's say there's one derivative, but it's made of these two partial derivatives. But let's say one derivative, and it is constant. So this is exactly what we know from calculus 1. Linear functions, derivative, yes?
I'm just wondering why, when we're doing z as a function of y, it's
Yeah.
still dz over dx.
My mistake, thank you.
Okay.
All right. So computationally, let's take this inside and quickly look at what this means computationally. So my function z equal. Okay, that's no problem. Z is equal to 2x plus y plus 1. Okay, so how do we get those partial derivatives which we computed by ratios? Instead, we look at the how do we do it using techniques of calculus 1 to end up with 2 and 1. Okay, these are the partial derivatives. Okay, but we certainly recognize them as the coefficients of the two variables. So the first one with respect to x is 2, and you can see 2 here. With respect to y, and you see 1 over there. So it is the coefficients of the of x and y. But it's really not a fair plan fair idea to try to use it as a plan, because, well, what if a function is not linear? Then there isn't really no coefficient to speak of, and the actual differentiation has to be involved, and we just have to have a right way of looking at it. How do we produce 2, but not by just simply observation as we did through differentiation? So how do I get 2 from this formula? What is this? It's a plus over here.
We consider y to be a constant?
Right. So for x, consider y constant. So you have to be explicit when you do differentiation. Partial differentiation, one of the variables, or all variables other than the one that you're interested in, assumed to be constant. So just take some getting used to. You declare y constant and then differentiate the rest as if it is like this, as if it is there is nothing going on here. So y is a constant, so it will disappear under differentiation. Right? Oops. Okay, so this is gone. This is gone, and that is gone. On the differentiation, with respect to x, everything is gone except to 2x. You differentiate 2x, and you have 2. Okay, so that is a better idea. Okay, similarly for y, consider or assume or declare x to be constant. And then your differentiation, which at this point becomes entirely exactly the same. This one, just as that one, 2x disappears because it is a constant, and then that's how we end up with 1. Differentiation is exactly the same. Okay, that's the last time I'm using this. Okay, so that's how we can get it. We can get it also through, and with this idea, we can now handle any function. And let me just take another look at our graph here to confirm the conclusion when we have more data than just 9. Okay, so if we carefully look at this, once again, we actually did it yesterday, so we try to progress from point to the next and ask ourselves what the slope is, what's the rate of changes. And so if I'm looking at the very top over here, so suppose I am right here, okay, and I'm going horizontally, and I see the change of x from 0 to 0.1, and the change of z from 1 to 1.2. So you just take the bottom will be the numerator, and the top will be the denominator, the difference of. So the numerator is 1.2 minus 1 is 0.2, the denominator is 0.1 minus 0, which is 0.1, and the slope is again 2. Okay, so we cut it in smaller pieces, but certainly the effect is exactly the same in the straight line. So the slope, no matter what segments you pick to evaluate the slope, the answer will be the same. So every time anywhere else you pick this, well, just to make sure I'm picking at random. So I'm doing this. Okay, the change is 0.2, while at the top the change is 0.1. Okay, so if we move horizontally, the rate of change is always the same, just 2. Okay, in the meantime, if we try to do it vertically, I say choose these, and the change is 0.1, but also over here, the corresponding value change of y is also 0.1. So if we go vertically, the change is always, the rate of change and the slope is always 1. Okay, so it's exactly the same thing, even though we have way more data. Okay, so we're more or less done with this function. So let's take a look at something more complicated when the original function is not linear, and therefore its partial derivatives will not be a constant anymore. Okay, so this is the function. Here it is. The function is in fact sine of xy. You can see it at the bottom. Okay, so there is some change. Otherwise, everything is very similar. So x is, I think I switched x and y here. Well, okay, well, let's just be careful with that. Not that it matters because it's symmetric, but you can see this how it is computed: sine of x on left and blue y on right. Okay, so let's just. I guess I put it this way in order to. I think I made that point before that if you want to have things like that, x here, y there, you'd better. This is a better arrangement because I can just do x and y. So if I flip it, x and y, right? So the way I did it on the other one is just not as familiar, even though it doesn't matter, it's data, so it doesn't matter where we put it. So x is red, and y, the red axis is x, the green axis is y, and the purple axis is z. Okay, so that's what the function looks like. So, okay, let's take it all the way through. And then what I just described with the linear function, every time produces the same number. Now I have to use the Excel carefully in order to produce the same result, but because so much data is going on, I have to make it. I can't do it by hand anymore. I cannot do it by simple examination because the rate of change might be different in different locations. And you can see, you can probably try to figure out, using what you remember from Calculus 1, to figure out what the partial derivatives would look like. And the idea is, you take the graph. Well, actually, its easiest way is to look at the one on the edge. So this is the y-axis. This is the very end of our surface, which so it is which one is it? It is this one. Okay, so this data over here at the very end is plotted like this. So the values of y are at the top still, but the value of z is here. So then you can look at it at this edge of the surface as a curve, and that curve is the graph of this function over here. So you could apply what you know from Calculus 1 in order to try to figure out what the function is. and that function is you can confirm at least confirm that indeed the behavior is, as you can see, it's positive, 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 which is 1, roughly somewhere, which is the highest point, then going down, crosses the x-axis or y-axis, and becomes negative, which is -1, and start growing again. Okay, so it certainly is a confirmation, and you can imagine what the derivative will roughly look like. What do you think the derivative should look like?
Cosine.
It is cosine. I mean, this is very much sine with a coefficient, but other than that, that's how you differentiate. So it will be cosine with a coefficient. Okay. So let's do it algebraically first. Because it's really not a lot of a challenge. So if you are comfortable with differentiation in principle, then starting partial differentiation is not a big deal. So my function f of x is sine xy. Okay, and once again, function of two variables. Okay. Function of two variables, sine of xy, so there's full symmetry. And once again, the plan is of differentiation right here for x, the partial derivative with respect to x. Consider y or declare y constant and treat it this way. Okay, so then y is it's a bit tricky, but you might remember from calculus 1 looking at various formulas that has a bunch of parameters. Okay, so for example, what could it be? Width times height times length. Okay, so you might be interested in the so that's the volume, right, of a box, and then you might be interested in the rate of change of the volume of the box as a function of height. Okay, so then what do? You treat W and L as parameters. They are unknown, unspecified parameters, and it is just a matter of point of view to think of them as not as variables that might vary and that you might be interested in the rate of change with respect to those variables, but rather you don't care about, you care only about one variable at a time. So these are parameters. Seems like just words. So this is a variable, and that these two are parameters. But the difference is crucial because then you go and you have your differentiation. dv with respect to that parameter that you only want, that you care about. If you do any kind of physics, and you are not motion necessarily, but any kind of physics. So you have here, you have volume, you have pressure, you have density, humidity, whatever, and they all involve. You have a formula with a bunch of variables, but you don't think of them as variables, but rather as parameters. You pick only one as a variable, and if you want to interested in the rate of change with respect to that variable, well, that's what you do. So dVdh is what? WL, right. So these are parameters, so you don't try to differentiate them. Another occurrence of something that superficially similar that you saw in Calc 1, so before I get to this, is related rates. So in that case, you have several variables, and they are sometimes called x and y. And then when you say, for example, you have something like this, and then you're supposed to find, remember this from calculus 1, find, say, what? UIDs. Okay? So very different. So never get confused these two. Why? What's the crucial difference? So it appears I have xy on the left, I have xy on the right. What's the crucial difference?
In the second one, there's a composition we use the chain rule to differentiate.
Right. Well, but why do we apply the chain rule? Well, let me carry it out. So I'm doing differentiation of this expression with respect to x. Okay. So I'll have. Okay. So what do I get? So ddx of xy squared is equal to ddx of 3. Okay, so this one is 0. Okay, well, what's happening on the left?
So just equal 1?
No, on left. This one, no, it's not 1, no. It is the product of two functions. So once again, forget about what we just talked about. I guess I didn't have to worry about you mixing up these two things if you just simply don't even remember all this stuff. So, well, maybe it is excessive, but since I started, let's finish it anyway. So what's the derivative?
2x y plus y
2x, okay. Y squared, right? So product rule, differentiate the first function, which is x. No, it's not.
No,
it's
2xy
x.
plus
Oh, are you, okay, let's start over. Okay, go on.
2xy,
2xy, yes.
and then plus y squared.
dy dx.
Y squared, dy,
No, do you
No,
want to be 2xy?
okay, oops. Okay, where's the variables? Okay, differentiate x, get 1, okay? And then do nothing with the other one. So 1 times, I don't know what's, 1 times y squared, okay, the first term. The second term is, we leave x alone and differentiate y squared, which gives me 2y dy dx, okay? And then it's equal to 0, so for dy dx, you got it, okay? So what's the difference from where we are at right now?
Well, on the left-hand side, y isn't a function of x.
That's the key. So related rates, what it means that there are two variables and they are related to each other. That equation over here is the relation between them. X and y are related. And that is why the rates are related too. But to begin with, the two variables are related to each other. In a new case, they are not related. X, y, not related. They are both independent variables. Both fully independent, and that's why we say that there are 2 degrees of freedom. If they are related, x related to y, it means that there is only one, there are 2 variables, but also one restriction, which means there is only 1 degree of freedom. Okay, so that's why this is a kind of curve. This is a curve on the xy plane. Okay, so that makes the whole thing one-dimensional. This gives me whole plane. So once again, this is a curve, maybe on the xy plane, and while this one is the whole xy plane. This whole xy plane is in plane. While here is only some kind of curve. I don't know what that is, but this is a curve. Okay, so the relation is the superficial relation should be overcome, and once again you fix x and you make y variable, or fix y makes x variable. That's how we do it. And like I said, the variables are unrelated to each other. Okay, so let's do that. So I say now y fixed, and I differentiate. This time, let me use the standard notation for partial derivatives. It has, instead of straight d's, it uses curved d's. Okay, so this is what we're supposed to find. A function, here will be a function of 2 variables, of this function of 2 variables with respect to x. In other words, the rate of change for every y on here, on the y-axis, and the function as it depends on x. So y, I mean, we're not going to fool ourselves. Y also is variable, right? But we just, for the purpose of this computation, we assume that it's not. It's not fixed. It's not variable. It is fixed, and we are y, because if we're moving horizontally, then it means that y is not changing. Okay, so certainly could go, if we go diagonally, that's tricky. But for the time being, either go vertically or horizontally, and algebraically it is very transparent. So let me put it this way. This is how we compute it. ddx. So that is very clear. The advantage of the Lagrange notation over the Leibniz notation is, if you remember those primes, you don't want to use as much of them anymore as in calculus 1, because you want to be very specific about the variable. If you have more than one variable, sometimes you don't know which one it is. You have to know what is that, what differentiation you do, x or y. So that's why this notation becomes this notation and that notation. Remember, that's called Leibniz notation. Is preferable. Okay, so and once again, these are curved D's. So how we'll compute? We take the formula for the for my function. That's not that's not a comma over here. Erase it. Okay. Oh, wait. So it's almost okay. XY, like this. Okay, so this is a notation for the partial derivative of x with respect to x. But here I don't want to deal with a partial anymore. I declared y fixed. And here I'm indicating with the denominator of my derivative that I'm going to be doing differentiation with respect to x. And I just remember that, well, x and y are near to each other once again there, which means that y is constant. So in that sense, then y serves as a coefficient, right? So what do we, how do we differentiate this with respect to x?
Y, I guess if we wanted to get the indicate the y as a constant, could we use y naught or y?
We could, and early on it's probably, in fact, a good idea. So why not say y is equal to y naught? This way we will be computing, and there will be no confusion. You know, if y naught, if you've seen it in calculus 2 especially, you put an index on something, and that probably indicates that you're talking about a specific value of that variable. So y naught, y1, and so on. So I put a 0 here, so we have y naught is just not a number. You can put a specific number. You can put a b there, so you know talking about a point a b, a is equal to x, x is equal to a, y is equal to b, and once again that might remind you that how to differentiate it. Unfortunately, it is very easy to get confused early on, but once you do this a few times, you'll be just fine. So how do we differentiate this sine of x times y naught?
Cosine x times.
Right, so can you quickly explain what the rule we use? Chain rule. Okay, so two composition of two functions, sine on the outside, x times y naught is on the inside. So remember in the product of two derivatives, so I have cosine x y naught times, and here I have the derivative once again. Let me write it out just in case x y naught, because this is the crucial part. So I differentiate with respect to x, this function x y naught, which gives me y naught. So the answer is y naught cosine x y naught. So y naught appears on the outside, and it gives you simply the stretch of cosine, a vertical stretch of cosine. Similarly, x is fixed. X is equal to y, x naught. And I'm looking at the curvy derivatives, curve d's, with respect to y. And now I indicate differentiation with respect to y of the same exact formula, except now I attach 0 to x as a constant. And the rest is exactly the same. Chain rule, differentiation, cosine, the same functions are involved except for that extra coefficient, x naught y. And here I multiply by the function, by the derivative of the function inside, which is d dy of x naught y. So what's the answer?
X naught cosine.
X naught cosine.
X naught y.
Right. So if I want to now throw out those dummy variables x naught, y naught, which we made up just to trick ourselves into thinking that these are not variables, just for convenience or just early on. a sneaky way to get around the preconception from calculus 1 if you just do too many differentiations then. So the answer is to produce the two derivatives explicitly. Okay? So do you have dx of x? It's a function of two variables. Okay, so we write them out now without those zeros, and we simply write them as y cosine xy. Okay, and the idea of dy of xy is x cosine xy. So you roughly know what these functions behave like. The fact that x is present here or y is there doesn't matter. These are purely functions of the variable. So if we are to study them, we study them in the exact same fashion as we study functions of two variables. So both of them are once again surfaces. So one surface produces two surfaces. So very, very different from what we saw with parametric curves. Well, but that's because we have so few functions. Just two functions, and produce, after differentiation, the result was two more functions. In other words, one parametric curve. And here, from one function of two variables, we get two functions of two variables. Well, you can imagine a function of three variables, it will produce what? Three functions of three variables. So, because differentiation will be with respect to each of the variables. Okay, so then you could try to utilize, for following calculus 1, utilize the idea of that derivative should tell you something about the behavior of the function. So we pretend that we did not see that picture just a minute ago of the graph of our function, and we could derive the features of that graph, not without difficulty, and the feature being the increasing behavior, but not in general, but in particular directions. So for example, say x, say how about y is larger than or equal to 0, x is between 0 and hold on a second, pi over 2, and let's see, pi over 2 as well. Suppose x and y are between pi over 2 and pi over 2. I think it isn't going to work. Zero and 1. How about this? Okay. Okay. 1. Okay, x and y between 0 and 1. Okay, so can we figure out anything from this formula about the behavior of the function? So what do we need to look at in this function and then that function in order to derive any conclusions about the graph of the original function?
So if we hold if we just pick some, say some x, if we hold x constant, we pick an x and hold x there, won't we get we'll get a space curve that lies along the surface?
Yeah, but I don't think you're looking at in the right direction. What I was talking about, remember calculus 1. How did we use derivatives? We actually did it yesterday with parametric curves. How we use derivatives to study the original function in calculus 1. Slopes, yes, but on its basic level, it's positive or negative. Increasing, decreasing. These are the basic things that you can say about the function is whether or not it's increasing or decreasing, and it is determined by whether the derivative is positive or negative. Okay, so we are in a very similar position, except we are specified the direction in which we progress along that surface. So we progress on that surface in the x direction. The monotonicity of that curve will be determined by this formula. So I intentionally picked x and y between 0 and 1 to suggest that I think it works out. So that y cosine xy is larger than or equal to 0. Okay, so when x and y between 0 and 1/2, it means that x times y is between 1 and 1/4, which means that cosine is positive. Cosine is positive, y is positive, the whole thing is positive, and the conclusion is that, so the partial derivative with respect to x is positive. It means that f, what do we say about f?
It's increasing.
Specifically, it is not a curve. It's not a curve. It's a surface. So how do we?
It's increasing in both, I mean,
We say it increases with respect to the x variable, but if you want to speak of a graph, it is increasing in the x direction or along the x-axis. Along the x-axis. Think about it as if we're talking about a terrain, okay, and then you could ask yourself, we're going up, we're going down, but you cannot say that unless you specify the direction. So here we're looking only two directions. We're going either north, or in this particular case, we're going east. If we're going east, are we going up or going down? The answer is we're going up. Okay, so the next question is, what about north? The answer is pretty much the same. So once again, x cosine xy larger than or equal to 0. F is increasing. Once again, but this time it is along the y-axis, but we will conclude that once again that if we're going north, we are climbing. If we are at the same time, we could reverse it and we can say if we're going south, we're going down. If we're going east, we are climbing. If we're going west, we are once again going downhill. Okay. So what remains is just to confirm. Let's get started. So this algebra, I want to confirm it. Well, let's confirm it first by looking at the graph. So we're talking about the top, x and y are fairly small numbers, so it will top square over there, okay? And it corresponds to where is the beginning of the, so the upper over here. This is the region we're talking about, and indeed, if you look at it, it's kind of flat, but not entirely. If we either go along the x-axis, red, or we go along the y-axis, which is green, we will be climbing slower and then faster and faster. But then the behavior certainly is changing. So what I want to do is next is I'm gonna create those functions from this data. Okay, so we'll be numerically differentiating by going horizontally one by one and producing more and more values and producing those two partial derivatives. Okay? All right, so we'll do it tomorrow.